All right, thank you for inviting me. First, I want to say that virtual conferences are suck and not to be, but okay, the reason why I'm trying to say this is that, Ranjay, it's so nice to see Ranjay here because Ranjay and I go back way long when we actually, the first time we met was like an internship at Google where we weren't like, in a research interaction. And so if I was doing this in person, I would be like, oh my God, we can go get a drink or something like this. But Alice, we are in our Zoom world. And so it's a message for like the junior students that it's going to be so much more fun if we're all in person. And so I really hope that it's next time I can see everybody in person. Okay, so I'm going to talk about this compositionality. I really like this topic. My title is going to be like compositionality in 3D humans, but actually we are, I would really like to get to where like Ranjay is at, right? But it's still very difficult to reconstruct people in the 3D world, but we're still making some progress towards it. And hopefully these kind of tools can be a way to, parse these videos on its own, because if you can understand how people are interacting with these objects in the 3D world, maybe you could label these actions and like order and story them together. Okay, but anyway, so I'm going to talk about two aspects of the compositionality that I'm looking at, or composing, two kinds of things that I'm going to look at. But let's just start with the kind of premise of all my research is that we live in a world that is 3D and dynamic and has full of people and animals and who are interacting with each other in the rich environment. And so in the as we approach a society where intelligent systems coexist with humans, it's very important that we are able to perceive and interpret what they're doing, what these people are doing with this environment, and so that we can interact with it. Okay, but this is still a very challenging problem because 3D reconstruction of especially non-rigid objects are super difficult. And so you can do this with motion capture, but you can't do this in the wild. You want to do this outside where you don't have to have these studios. And so much of my research has been about able to do this 3D reconstruction in the wild or ordinary videos and images. And so that's what we've been working on, this kind of 3D reconstruction of meshes from everyday photos or videos. And so there's been a lot of progress in this domain. I'm just only highlighting my work, but there's like really a lot of progress in 3D human perception. And so really the question is, what is next? And this starts to touch on the compositional aspect that the scene is really composed of many elements, not just humans, And it's important. Humans are very special subjects that we're very interested in. And so it's okay to kind of have a very focused approach in it. But these approaches are starting to do something. And I think to move on to the next stage, we really have to start considering the scenes holistically and not only think about the 3D human bodies, but reason what they are doing in the scene with who and other people and other objects. Another aspect that I would like to touch upon this, because this workshop is also about multimodality, is that of music or other types of multimodal inputs like context. And for one thing, obviously there's a lot of semantics and speech and such, but like to study this in the beginning, let me ruin your day. Let me ruin your day by playing this music so that it sticks with you for the whole day. But so there's a lot of people like to really dance, and there's this kind of multimodality aspect in how the body reacts to audio. And so we're going to look at it in this very simplified music setup. And so today I'm going to talk about our latest developments in composing humans and objects in terms of hands and objects, and how the hands are manipulating things in the wild, and about how you can use music to condition your 3D body generation. Okay, all right. So last year, so today I'm going to talk about this work that we presented at ICCV, this conference on reconstructing hand-object interactions in the wild, led by Za, Kao, and Ilya. I'm sorry, I can't pronounce your last name. And then Malik. Okay, all right. So last year, or last ECCV, we started working on this reconstructing 3D humans and objects. And I must actually show this picture, because the thing is, when I show this result, you're like, obviously that is the right interpretation. But the thing is, in 3D, there's a lot of solutions that can be projected the exact same input images, and there's so many of them. But for us, for example, the bottom result where the man is sitting on the bench and people are riding on the bicycle is so obvious that you're like, what are the other types of ambiguity that could arise? And so if you naively try to compose these humans and objects together, what you get is like the interpretation above, where the man is floating in the air and not really sitting on this bench. And all of these things, both of these images equally project to this 3D image. And so why does this happen? And this is really the fundamental skill ambiguity in going from 3D or understanding 3D things from 2D. And here is a visualization that kind of describes this. So there is a man riding a surfboard here, and we would like to reconstruct the body and the surfboard. However, you can see that if you shoot away from this camera, there could be infinite possible combinations of this surfboard and the human. So basically, the surfboard could be super tiny and very close to the image, or super huge and then really far away from the camera. And of course, there's not, for us, it's very clear what it's supposed to be because this human is interacting with it. So the point of this, our paper in ECCD, was to show that to resolve this ambiguity, you need a couple of things. How do we humans actually disambiguate this? Well, first of all, we have common sense. Well, we have a lot of knowledge about the world, but obviously there's a lot of things, like you can't have a tiny surfboard floating in front of the camera. But aside from that, you also have this common sense of how big a surfboard is going to be. They're not going to be like a building size, or they're not going to be tiny sizes. So you have these expectations on how big these objects are, which really narrow down the possibility of what the objects, where it could be. And another thing is, so that's kind of showing the reasonable surfboard sizes that really kind of narrows down the search. And then the second thing is the fact that the human is interacting with the object. And so then it has to be that the board has to be near the humans. And that's one way to get to the right answer. And that's reasoning about how they interact. And so we kind of showed this, demonstrated this approach and tried to put it together. And now in the follow-up direction, we're thinking about the same problem, but in the more complex scenario of hands and objects interacting with each other, and kind of building a little bit more on this, how humans and objects interact, and putting a little bit more prior on this. So this problem of reconstructing hands and objects is a really important problem, because if you can understand how humans are interacting with objects, like, how I'm grasping all of these things, it would be great for our robots to go in and interact and pick up stuff for you in the real world. And so there's been a lot of work in this direction, and there's a lot of lab collected data set. However, again, the challenge is that in videos like Epic Kitchen or these Eagle 4D that was recently just released, none of these images really look like, not only egocentric, but all these videos from the internet, none of these really look like, it's a lot more complex. It doesn't really look like data sets that's collected in the lab with grad students showing us how to do these things. In reality, hands are much smaller. There's a lot more clutter. There's a lot of motion and all of these stuff going on. So this is really challenging. But we want to start looking at things in the wild, because I think that's where really the challenge is going to be. And if you can parse these YouTube videos into humans and objects, there's a lot of things we can do. So because this is a super hard problem, in this work, the general strategy that we've been taking for human objects is that, we try to reconstruct the objects, but we use an existing CAD database for the shape problem. And then we will leverage the 2D image cues and the 3D priors to do this reconstruction. So the interesting really thing about it is that humans are difficult because they're non-rigid, but because they are also one category, there's been a lot of work on this. Now, on the other hand, man-made objects are rigid. So if you had lots of multiple views, it's much easier to reconstruct them. However, they are so much more diverse that actually reconstructing these objects in the wild is currently a lot more challenging than reconstructing humans. Anyway, so that's why we kind of use these CAD models, but this is our approach called the role reconstructing hands and objects interaction. So this is the framework. So first, in the beginning, we get this hand pose estimation. For this, we follow the standard practices. We kind of have like a regression-based approach that predicts where the hands are in the beginning, like HMR, the type approaches. And then you take these 2D key points and you can like do some another simplified like refinement to fit these 3D key points to align to these 2D key points. Once we get the hand, next is the object. And so for this, we will know that like we'll assume that we know which object CAD models are available or like are the right things in the image. And once we have the CAD model, we're also going to use all the possible available tools in our toolkit. So we're going to use methods like point rend or mask RCNN to give us these masks of these cropped objects. And then we're going to basically do a lot of initializations on these of the CAD models on top of these images, and then optimize the 6DOF pose, so the rotation and the translation of the objects to explain the mask, as you can see over here. So there are a couple of results that you can see, and you can rank them by how well they explain the masks. Okay, and then once you have the initializing hands and objects, we can do joint optimizations to make sure that they are coherent. And by this, what we mean is that we're going to avoid interpenetration. And we're going to move hands and objects closer together. So this is like the prior that was saying, if humans and hands are interacting together, then they should be touching. And you also want to preserve the ordering of the semantic segmentation to account for a reason about occlusion. So these are kind of similar losses that we introduced in the ECCV paper. Although like each and every one of these steps had to slightly be modified for the problem of humans and hands and objects, because it's a little bit harder. And then we also have this final pose refinement module, which is inspired by this GrabNet in this paper, Grab, which is a data set that collected a lot of hands and objects in motion capture. But this really provides us with a lot of great hand object priors. And so you can train like a VAE-like model that gives that given hands and objects can refine like the vertices or like interactions of the hands and objects. And so this really kind of takes us like the final level, because optimization would give you something like rigid, and then by prior it will really give you the pose that is kind of more reasonable. So here are some intermediate results. So let's see. So in the beginning, when you just do individual optimizations one by one, you get these results where, hands and objects are, roughly in the pose and the scene, but they're like super far away from each other because there's so much ambiguities about their scenes scale. Now, after doing the joint optimization, we are able to place them in the similar proximity. And then lastly, by adding this refinement on the hand pose interaction, you get this nice, more realistic, really adds this photo, like a kind of realism in the way the hands and objects are interacting with each other. So let me just show you many results on these videos. And these are images that we obtained from the internet, like the vlog data set and 100 Days of Hands, and also some Epic Kitchen. And we are able to recover hands and objects interacting with these diverse types of objects. Toothbrush and the pencils and these darts also, and many various kinds of interactions. So I think this is really the cool part of internet video, because there's a lot of ways in which people interact with these objects. Okay, so now one of the other, so in order to make a progress in this direction, I think you should be asking me, like, where are these CAD models coming from? How are you really obtaining this? So to make progress in this direction, we built upon this optimization strategy that we developed to create a new data set using our method and the human intervention. So basically what we do is we get some of these reconstruction by running our approach. And then later we have an interface where humans can manually fix the errors. And that way we can actually get like a pretty good ground truth on these images. And this data set, we collected about 500 images and annotated them. And this consists of the image and the 3D meshes. Because we've done the reconstruction, we can also recover the A-modal mask, as in like completed masks of each of these objects. And then we can also reason about which parts are in contact between the hands and the object. So in order to do this, we went ahead, and I think this is one of the most important aspects, is that we collected a lot of different kinds of CAD models, because objects are super diverse and really long tail also. But we basically have a lot of different kinds of CAD models. So this was, originally mined by humans by looking at these images and suggesting which kind of CAD models best match each of these images. And this long tail nature of this data is really interesting. And so this data set gives you this kind of variety. And once we have this, we used our approach to get a really more nice reconstructions on these in the wild images. And so we have this high quality 3D hand and object reconstructions on 500 images. Ours is captured in the wild. We only have images. We have quite a diverse number of participants because our data is mined from the wild. And most importantly, the number of objects in our data set is much larger than the other one, which tends to be the bottleneck. And we run this on Epic Kitchen and mostly on 100 days of hands. So here are some results. And so these results are the ones where humans have like made sure that made some final adjustments. And we have these, so yeah, so these are really, I think these are very interesting to watch, and different ways in which people can interact. That's difficult. Okay, all right. So once we have this data set, we can do kind of nice analysis of how hands and objects are interacting with each other. So this is like an ISO map of showing the hand poses, embedding by the hand poses, but then you color it by hand object interaction, which we automatically get from these objects and then the hands category. And so we can see there's a lot of interesting things that's happening in this collection of 500 images, which is that, we have this same object category of pens with similar hand poses. Naturally, people use pens in similar ways. We can see this, but then we can also see that there are different object categories that are used with similar hand poses. So this is grasping, I guess. And of course, there are also situations where there are same object category of pens, but people are using in different ways to use objects. Because we're embedding by hand poses, you can see that we've discovered this direction of like hand closure. And so there's a lot of interesting analysis that you can do on this data set, and hopefully this is useful. So in summary, we propose RHO, which is reconstructing hands and object interaction for single images in the wild. And we use this technique with human intervention to create a new data set in the wild, which we call manipulating objects in the wild. This is really at the final stages. Like we're just writing readmes and stuff like this. So please send us an email if you want the data, and it will be public very soon. Okay, so that is one aspect of compositionality, which is to understand how hands and objects and humans and objects interact in the wild, or how to explain the image as a composition of hands and object. Another aspect that was talked about, another aspect of this workshop was multimodality. And so I would like to talk about this direction, which is how do we generate motion given some other multimodal cues like audio. So that's the dancing video. Everybody loves to dance. Dancing is a universal language. And so the question is, how can we learn to dance to music? Now, this is also very closely related to the problem of human dynamics or human motion prediction. And we've been working on this direction. And there's a lot of work in this. So for example, classic works in 3D motion in graphics world has this technique called motion graphs, which is basically a nearest neighbor matching in construction of a graph using similarity of the hand body poses, and this allows you to really just kind of interpolate existing poses and create a lot of things. And also people have been looking at a lot of like, given past 3D human poses, how do you really generate a 3D motion synthesis? And this is very related. But the problem of the 3D human motion synthesis has also been studied on its own. But as we know, motion is always task or goal dependent. And so it would be nice if you can specify the task or the goal in one way or the other. And I really believe in, as we develop this approach, get more complex data sets, the kind of context in which that defines human motion is going to be the environment, or what's in the image, constraints in the environment. You can tell people are going to pick it up, or, if they're cooking, they're going to go to the refrigerator because you see the fridge and people are probably going to go to the fridge. So it's really interesting to think about how can you condition, like add some context when you predict the human motion. And in this aspect, I think music is really nice because it's a kind of dense kind of like a guidance, but it's also, and not exactly specifying what the motion should be. And so this allows us to tackle this problem of motion synthesis in a way that is contextual. Of course, there's a lot of sequence-to-sequence approach that can generate very cool, results for language and audio. And these are often like clip or, cross-modal, like text to image. And so it's very related to our approach. But we will show that naively applying these approaches to these problems don't necessarily really work. And of course, I do want to mention that there's been a lot of works in people that do audio to 2D motion. So there's this works that does speech to gesture or dancing to music in 2D. We compare these approaches, so these tend to be 2D motion. And if you have it in 3D, it's really nice because you can easily transfer these 3D motions to new avatars, as you will see. Okay. So the reason why this is a really challenging problem is, of course, the lack of data is one. And then also generating dance motion that is correlated to music is very challenging, actually, because music and dancing is very weak correlation, in a sense, like, you can turn off the music and just looking at the way that you were dancing before, you can probably keep on dancing. And this is very easy. Network likes to cheat this way. And so we had to do a lot of details in the model in order to not make this work. And also another challenge is, autoregressive motion generations tend to really drift. The more you run it, the longer you run the model, the more it starts freezing or starts going crazy. And so we basically find out that, it's very important. The details are very important. And I'll talk about a couple of key aspects in order to make this motion generation much better, like train a model and a much small details that really matters. Okay, so for the data set, we collected this, we built on this really nice existing database from AIST, where they have 9 cameras and have lots of dancers, multiple or just single, multiple levels of difficulties of dance. And so this was an existing database. And so we really like this data set. Oh, this is great. And it has a lot of music. And note that this one is kind of in an instructional mode, in a sense that there's a lot of different types of dance over the same music, right? Because there's like an easy dance and a more advanced dance. And so this isn't like every single dance has a single pose, single dance, but there's different dancers dance to the same music, basically. And so this is a diverse, like, one-to-many problem, and it's not it's more realistic. I think it's a nice setup. But then this data set wasn't 3D, like it has 9 views, but they're not calibrated. It has people, but it doesn't have any labels on the people. And so what we did was to apply the standard best practices system by putting all of our current knowledge together, which is to do key point detection and do camera estimation, calibrate the camera, triangulate these 2D key points to make them into 3D, and do bundle adjustment over time to refine them. And once we have them, we can do this fit the simple human body model to recover the joint angles and do basically inverse kinematics on these 3D key points, and so forth. And this is, we have all of these developed tools, but putting them together is not really trivial. And we did this, and the code is open sourced. And the result of this we call the AIST++ dataset. And so this has all of these nice new additional annotations on the AIST dataset. Another nice thing about this dataset is that it has a lot of different kinds of dance style or genre, you can see. And also has lots of subjects, which is nice, or like, more than, 1 or 2 dancers, collecting this kind of data is difficult. And so this is our data, and it contains both the 3D motion and music at larger scale than previous ones. And it also has a lot of views and images and subjects and human 3.6M also. So this is available now. So I hope everybody can use it, and for many other reasons, many other purposes, just other than this dance generation. All right. Now on to the model. So how do we really formulate this problem? So the way we formulate this problem is to generate, the goal is to generate long motion conditioned on music. And so what we have during the training is that we have an input music, an input seed motion. This is an autoregressive model. So this is why we have always have some motion existing from the past. You have to look at your past motion movement as well as the new music and then change your motion. Okay, and then during training, we train this model to output this motion given input, and we just do this many times. And at this time, what we do is you take this input seed and the input music, which includes the future, and then we predict the output, the motion. We only take the first predicted future and then append it and make it as an input, and then run this in an autoregressive manner to generate new types of dance music. In terms of the motion generation, motion representation, we model the joint angles of simple in terms of rotation. And we also do the global root orientation to figure out where they're looking at. And most importantly, we also add the global translation, which is that how are the humans moving in the 3D world? Like a lot of the existing works not necessarily output the global translation, because if you're, this is a hard problem. Like a lot of us were studying it, fix the root. How is the how is the kinematics of the human changing? But when it comes to dancing, if you're not really actually moving around, it doesn't look like dancing. And so it's very important to capture the global translation. And actually, global translation is the first order explanation of where the humans are and doing. So I think it's actually very important to predict the global translation. Anyway, so that's our motion representation. And so here is our architecture, which is based on transformers, and it sounds simple, which is that, you take each of these modalities and on its own transformer, which encodes it, and we're going to encode it into the same token, the same representation. And then so we're just going to concatenate these inputs along the time directions, or just treat them as sets elements, and then send it to a cross-modal transformer, which basically just, doesn't distinguish whether they are a motion or audio tokens, and then just output the motion directly. Now this looks simple enough. Oh, and then you use the ground truth loss to supervise this. Now this looks simple enough, but the devil is really in the details. If you naively apply a GPT style, like a vanilla, an autoregressive transformer, which what the previous work has done, actually this model doesn't really work so well. It really starts freezing in the middle, or generates unrealistic motion. And then we were struggling with this, and I think the reason why it works in a language has a couple of different reasons. Like I think the contextual window is much longer in language and it matters. And most importantly, actually, language is discretized representation. So you never really go off the manifold, as opposed to here we are trying to, regress to the continual representation of the 3D motion, which is much harder. Another reason in language it has to be in this GPT style is because the window is so long, you don't want to have to, you have to be able to efficiently add efficiently run this process. But what we found out that this masked attention is not ideal, because if you're trying to predict what the motion should be, you really want to incorporate like emotions to really look at each other. The past motion should be able to look at what the future motion was doing. And so this is kind of like BERT style encoder, you might say. It's like a full attention is important to do this. And then not only that, well, now that if you do a full attention, you can't actually do this GPT style of like immediately predict the next token for every single node, which is efficient in training. But if you made it into a full attention, you would have already seen the next thing, right? And so what you do once you move into this full attention is that you start predicting the one after all of the current field of view, just like other type of predictions, n+1 to n+n. And we actually found that not just predicting the next immediate motion, but predicting future makes a very big difference, because if you have to predict out into n future, you really have to look at the context of what's going on, as opposed to if you just have to predict the immediate next future, then you might just have to copy or do some small adjustment from the past, and it would look reasonable. So this is the experiments that we did, which is that this is the vanilla GPT style, and you change it into full attention, but only predict the n+1. It's also not that great, but predicting up till 10 futures from M really improved the results significantly. And then we can also keep on predicting longer also. But here are some, let me just show you visualizations. So you see that this is the GPT style model, and it starts not moving after a while, it regresses. And then the full attention model actually is able to keep on going. But as you can see, it's a little messed up. It's not really looking at the past motion, or like, it's not really coherent. But the model that is trained to predict 20 into future looks a lot more realistic. And so this makes a big difference. And so it's something to really explore. If you're training using transformers on this kind of tasks, you can try it out. Okay, and please let us know if you find this kind of these kind of things that make a difference. Okay, so now we were able to actually change transformers to actually generate long motion, which is great. And then the next failure mode that we had was that because music is a really weak correlation and some level of dance is already in the seed motion, that network really kind of like didn't really pay attention to music. And so what happened was that in the beginning, we were doing some kind of late fusion. So you have like a long transformer, like deeper transformers for each of the modalities. And then we do a very shallow cross-modal transformation, the close-modal transformer, which is one of the prior work I was doing. And then, there's a simple option, which is to do early fusion, which is to have shallow encoder for each single mode, but then do a very deep cross-modal transformer. And so this makes a big difference. And so this is the attention map. So x-axis are the tokens. So they're like, you have the seed motion and then the seed music. Okay. And you can see that if you're doing a late fusion model, it's really not paying attention to music, and it's really looking at, the motion, and then it's trying to predict the motion, just giving the motion. But if you do early fusion, then it starts paying attention to the music as well. And this reflects, so that's the same picture. So basically, this is very important. If you do early fusion, the sorry, if you do late fusion, it really ignores the music, and if you do early fusion, basically, then it really has this model that can change their dance with the music. And so there's some numbers, but let's just look at the results. So here are, I'm gonna show you. So these two models are conditioned with the same seed, but the music is different. Okay. Okay, and so yeah, and when we do our testing, we actually take random seeds too. So the seed may not always necessarily match with the music, as you just saw, but the model can basically pay attention to music and then change the dancing style, which is encouraging. You really want to see this happen. So here are some comparison to prior work. So Dataset is an LSTM encoder plus transformer-based model. Liadal is also a very similar model. This is deep fusion transformer model. And then they tried to discretize their output because to make it more like the language problem, which is a good idea. But because of this, it's not very coherent. And our approach is able to generate the most coherent option. We also, there's a lot of work in 2D based music dance generation. So we also compare with this, but just simply replace the motion representation into 3D key points instead of just 2D points. So previous approaches were all 3D approaches. So if you're 3D approach, then you can just use the joint angles, and then the data isn't simple, but you can use these avatars to just retarget the motion. 2D key points approaches don't give you angles, so you can't use these characters to retarget it. You can only show it in skeletons. But basically, we trained our model with 3D key points also, and then we adjusted the code to deal with 3D key points. And then, and the thing is, our approach is still deterministic. We need to make this multimodal. I mean, able to predict multiple motions. But the thing is that we actually have the seed as well as the motion, a seed as well as the music. And so we are able to actually generate different dance for same music by changing the seed initializations. There are a couple of prior work that is not autoregressive that directly predicts the motion from music without any seed conditioning. And they know these approaches, because AIST has multiple dancers dancing to the same music. If you do directed deterministic mapping between the music and the dance, the model gets really confused because there are multiple ways people are dancing to the same music. And so the seed is very important. Yeah, so these models really don't know what to do because there are multiple different ways, and ours you can distinguish by the seed motion. Okay, all right. So the question is like, how do we evaluate this? It's a very difficult problem. We provide this alignment with music metric. So this is like the audio signal, and then you can look at the discontinuities in the audio signal to find where the music beats are, which is in orange. And then you can also look at this is the kinematic velocity. Okay, so this is the kinematic velocity. You can do the same thing to the music, the audio, and then get the music beat, which is in orange. And you want to make sure that the kinematic beat, which is just discontinuities in these signals, aligned with the music beat. And so it's good if this green and the orange are together, that means, you're kind of like on the beat. And then it's not really necessary that you're always on the beat. So it doesn't have to be that for every single music beat, there has to be a kinematic beat, but we evaluate such that for every kinematic beat, you really hope there's a music beat. And then we do motion distribution matching. It's kind of like FID, but without an inception. We call it FID, we should call it a KL divergence of the motion distributions. And we use traditional motion features from fair motion to do this. And then we also measure the diversity in motion to make sure that the model is not outputting a single dance. We do show what the diversity of the original ground truth data set is. And so you want to get close to this number, but then also be realistic. And so some approaches are very diverse, but then doesn't look very realistic. And so we're kind of like in the middle. I think there's still much further ways to improve this model. Lastly, we also did user study by asking, A/B testing our approach with the real data, which is challenging, although we were able to fool people 25% of the times, and then with these corresponding baselines, which we significantly outperform these other parts. We also tried to make sure that the people that we ask, the demographics of the participants are well distributed, and we wanted to make sure that we get some real dancers. Okay, so let's just see some more results. Yeah, so here's some fun results, and this is a really fun project because one of the co-authors, Shan Yang, is a dancer, and then this is why she was inspired to start this project. And so I think it's a really cool examples of how you can use your hobbies to improve, to get ideas for your research. So we presented the system that regenerates much more realistic and long motion than prior approach, but there's a lot of improvements to be had. So for example, as you can see, the motion, it looks good, but it's a little repetitive, and it doesn't really kind of like change different types of motion. So that would be really nice. And I think that's a function of our representation. It's continuous right now. And I think doing something like, VQ or something more, discrete, I think would really be nice. It's still deterministic. And so we want to model, the multimodal aspect properly, although we can generate different dance by changing the seed or the seed. It would be good to model contact and the physics also so that it, looks more realistic. And then add other multimodal conditions, other types of speech or instructions to generate different kind of data. And I really mean it, and it doesn't have to be just for the dance project, but I think this generic framework is important in generating realistic human motion from some context. Okay, with that, okay, shut up, it's quiet. Okay, with this, I'd like to thank my team again, and take any questions.
Thank you, Angjoo. I think we don't have Konstantinos still, so I'm here. So if there's any question from the audience, raise your hand and let me know if you do have any. Could you start with one while we're waiting?
Yeah, I can ask a question. Quickly. I think this is super cool. And it's also like a really fun presentation to give with tons of videos and stuff, which is really, really enjoyable to watch. I'm wondering about the seed. I feel like one of the things that maybe you've already thought about is thinking about incorporating the level of difficulty of a dance or the type of dancer, perhaps their identity, into some sort of embedding and using that to condition on. Have you tried anything like that? It'd be
Yeah,
fun to sort of,
yeah. No, that
because
would
I was thinking about comparing this to the Maya project, which is this chess project, where they try to figure out what's your ELO rating and then condition on that ELO rating to figure out how that person at that level would play. And so what you can then do is also turn this into a whole teaching paradigm where you could say, okay, if you're a beginner, what's something that you might not do, but someone just a level above you would do? And then could you suggest improvements to a given dance or something?
Yeah. That's a great idea. That's a great idea. We can basically do like layperson dance, like, beginner dance to like professional dance. Actually, that is possible. I think that data set has that kind of potential because it does have that kind of leveling and advanced. I think one thing is that the advanced dances are like very, very advanced and like lots of like moving around in the scene. So I think we do reconstruct some of them, but I think we kind of focused a little bit more on the easier aspect of this. But yeah, that kind of contextual conditioning, I think would be a really cool way to go. Yeah. And it would also align for other tasks also.
And the other thing that came to mind was, how would people use something like this? And one very simple, perhaps, thing to try would be, when I've seen people trying to choreograph dances, I'm by far not a dancer. So when I've seen that happen, usually there's segments that they do, and then they fill in gaps in between. And I wonder if you could turn this entire process into not just something that's autoregressive, but maybe filling in parts in between where people can identify, these are the trajectories I want to do at these sort of time steps. What can I do in between, given like these two beginning and ending poses?
Yeah, no, that would be really good. That would be a lot more like real, like, choreographying. Yeah. And I think that would be nice. And actually there is a concurrent work at SIGGRAPH that actually kind of goes in that direction, because so that like people can specify more. And to do that, I guess you just need a data set with a lot more kind of labels on like what kind of path these things were, although we could actually generate that.
Could extract it from the beats, right?
Yeah, we could extract it from the beat. So that would be a really cool direction. They had, I don't know if you know, like this Hatsune Miku, like these like artists in Japan, like people just make these like virtual dances and they've already choreographed everything. So that was the data they used, and it was really like there was a lot of labels on this, so they were able to do that. But yeah, that kind of direction I think would be really nice. And this motion in betweening, I think it's a really cool problem. And there are a couple of people who are looking at this, but it's mostly for kind of periodic motions, like, running, kind of things, kind of poses, and you want to generate the in-betweens. I think it would be cool to do a lot more complex ones.
Yeah, and the final thing is, obviously this is really hard to evaluate. I think the metric that you have with the beats is a really good one, first of all, because I think that's one of the first things that people probably think of when they think about dancing, are you on beat? And the human evaluation is also really, really interesting. I wonder, as people make progress on something like this, how would you evaluate one dance to be better than another, assuming that they all have the same beats lined up and they all look realistic, but how would one be considered better at that point?
Yeah, that's a good question. Yeah, maybe the complexity then, yeah, like the repetitiveness of like, I think you can start, I think the real dance looks a lot more like, there's a part A, part B, part D, and then part C, and then go back to part A and part B, because that kind of dance. Actually, there's many different types of dances actually, but one specific type of dance might be that way. And so it would be nice to have that kind of like some structure in the dance,
compositional dance.
Compositional dance, yes, compositionality. Yes, you could have like a dance graph or something like this, You really do want some kind of graph like that, and then maybe that's one way to make it better. Yeah.
Yeah, no, thank you. This is pretty cool work. Obviously, tons of things you can potentially do moving forward from this direction. So yeah, it was fun listening to it.
Thank you.
Absolutely, yes. I got a quick question regarding the hand object interaction work you presented. Very interesting work. I was looking at the paper in the conference and also the the video, I think, and I saw the failure cases. And I think was it in the video or the paper that I read that the failure cases, and you actually mentioned it too, in many cases, it was either the pose estimation failure or the interaction discovery failure.
Yes.
So the thing is that so this work compared to other compositionality works, interaction type of discovery works that we are doing, it depends on a very like complicated task, and other tasks like pose estimation, which is actually itself still a challenging problem, especially in 3D. So I was trying to see, or at least I was just wondering, which one is you think is more challenging, or you had problems with in the failure cases? Is it like discovering the interaction, or the pose estimation was the major challenge to begin with?
I think the major challenge is that in the wild, because the objects are so when there's a lot of interaction and clutter, like much of the object is like occluded. And
Already.
So like, for example, if there's like a knife, but then there's like a pieces of it. So like basically like pointer end or mask Gaussian gives us these like modal masks, right? Like just a tiny bit. If you can only see a tiny bit of this, then this fitting of the objects are completely off. And when the objects are so far away, there's not that much you can do to recover it. And so that's the challenging part, I think, the clutter. But this is also the reason why you really need to start working with the clutter so you can actually solve these problems in the future. And I think objects are starting to be the bottleneck, I think, really, right? Because you also have to start figuring out what the objects are. And another thing I really didn't really talk about is that we have many different kind of object types. And then like masked Gaussian doesn't really have, I'm sure robotics people have said this, but masked Gaussian doesn't have like hammer or wrench or like these different stuff. And like what we actually do is like, they don't have that category, but we kind of just look at the high responses, like highest responses, no matter what the category is, because sometimes it gets it. And so that's how we're doing it. But the diversity of the object is, I think, one of the most challenging aspects. And I'm really excited for this like new data sets, like the Eagle, like the 4D data sets. Hopefully that can kind of give us more data to kind of restrict these directions.
Absolutely, yes, thank you. So any other questions from the rest of the audience? Okay. You have Sarah, right?
Yeah, thank you for this nice presentation. I was wondering, for the dance work, so do you enforce in some way that a generated dance is in a specific style, or do styles get mixed? Or
no, we don't do any styles right now. So I think, you know, that's one of the, I think it would be really cool to do specification based on some kind of like attributes like that. In fact, it's not impossible, I think, with this data set, but basically, well, there aren't other actually labels like that. I mean, I guess that's why we could have used advanced to beginner. I think that was one thing that we could have used, but it basically just has 10 different genres of music, and so we're kind of just using the music to specify it.
I think in your videos, I also saw things like ballet or popping, or right?
Yeah.
So all these videos are labeled with those types of styles.
Genres, yeah.
Okay, yeah.
It's a nice data set.
And when you evaluated the results, did you see that the music matched with these types of genres, or do you have any idea about that?
Yeah, so the beat alignment kind of touches upon that. And so if the music is like a ballet slow music, and if it's generating like a hip hop music, it won't really match the beat alignment. I guess you could have like danced slowly, like you did a hip hop dance slowly. We don't really actually touch on that yet.
Okay.
Yeah. But
Thank
also
you.
another thing I want to add is that this data set is a good question, is that this data set, the genre is really good, but it's also quite like fine grained. And so like there's like two kind of like slower dance, and like the rest of the 8 is like very specific type of hip hop dances that I can't really tell a difference about actually. So that's kind of one thing to note.
Okay, thank you.
Thank you.